Hi everyone. First of all, thank you for coming to this talk. Um, so this talks about OCaml's effect handlers, and I think I understand there's like a lot to cover, and this is very unfamiliar for a lot of people. I'll try my best to incrementally get there. So quickly about myself, I'm Manas. You may know me as Promethean Sacrifice, as I do a lot of open source work for Reason and OCaml. I run a small company that is focused on OCaml to help build OCaml developer tools, and I have been maintaining the Easy Package Manager, which works to manage dependencies in the Reason, OCaml, C, and JavaScript packages. Um, so professionally, I worked for the Lego compiler, which is a smart contract compiler for the Tezos blockchain. I helped them set up developer tools like package management and multi-platform builds, etc. And I've also worked a little bit on the Tezos economic protocol, which is written in OCaml. Currently, I'm trying to help a company set up an OCaml team. So, question is, I'm assuming a lot of people would have heard of OCaml already because LLVM already has like an OCaml tutorial to get started with writing a compiler with LLVM. Nevertheless, just to be, and I'm sure there's like a lot of hype these days around on social media regarding OCaml with the recent multi-core release. Let me quickly go through what it is, what makes OCaml different from a lot of languages. Maybe not so anymore, but it's the type system. It comes from an ML family. ML as in nothing to do with the machine learning, but meta language. And it's known for its Hindley-Miller type system. It's geared towards a functional programming audience, like Haskell in a manner of speaking, but closer to Metal, I'd say, because of certain features that it doesn't provide like Haskell. Here's like a quick example of what parser combinators look like in OCaml. I believe many of us are familiar with generated parsers from tools like Yak, Bison, or whatever. But the functional programmers are also quite used to the idea of writing handwritten parsers with building them from simple parsers to all the way up to more and more complex parsers with parser combinators. OCaml is different from Haskell in the sense that it is more eager and it is imperative. And by imperative, if you're a C programmer, you'll have an easier time writing OCaml than Haskell. So it should, and for a JavaScript or a Lisp hacker, it should seem much more familiar because OCaml has very similar ideology when it comes to expressing functional code. Unfortunately, the syntax highlighting is off here, but here's an example of, here's some OCaml code written in Reason syntax. As you can see, it looks very similar to JavaScript. When this would be run, you'd see how the compiler's type checker works with this. And yes, it has classes too, but we'll try not to get too much into that today. If you're curious, this is what an example of a class would look like in OCaml. Again, this uses the Reason syntax. I know this was a very quick and brief introduction to OCaml, and I'd like to quickly get into why I'm interested or I'm trying to talk to you all about the new effect handlers feature of OCaml, or more on that. So first of all, how did I get introduced to this topic? It was because as I said, I tried to work on a lot of developer tools for OCaml, one of which was the debugger, which emits dwarf 5 output. When one has to understand how the stack frames are created, you have to, so that you can emit better dwarf 5 output, you have to have a very deep understanding of how the runtime manages stack frames in OCaml. So next, let me quickly talk about what effect handlers are. If you're a front-end developer, you probably have heard a lot of hype around this topic called algebraic effects. Algebraic effects is one approach to modeling computations, effectful computations. OCaml has taken a very pragmatic approach to sort of implement the algebraic effects described by Martina Pretnar and others. And by that, I mean it has not gone all the way in to implement everything that they have described in their paper, but a nice little middle ground to make sure you can write better concurrent programs. Because, I mean, of course, we all understand how ubiquitous concurrency is in our programs. So OCaml's goal was to make sure you can have expressive concurrency primitives, especially with the recent multi-core release, which is going to make things very exciting for OCaml programmers. Uh, quickly giving time, let me try to give you an intuition as to what effect handlers are. Very simply put, I'm sure all of us here are familiar with try catches or try catch exceptions. You know that even if you have statements after throwing an error, they simply get skipped and you straight away enter the catch handler. What effect handlers is basically resumable exceptions. That's like the best, simplest way to understand what effect handlers are. It's just saying that if you are able to throw at one point, can you handle it and get back to the point where you threw? And you might ask why that's useful. Short answer is you can model a lot of computational effects and make your programs look pure. Why purity? I think front-end developers are today sold on the idea of purity in their functions at least. So especially with React making your UI as pure functions of your data. So with that said, let's try to quickly look at what OCaml effect handlers in OCaml look like. By the way, when I prepared the presentation, OCaml did not have native syntax for effect handlers, but as of few days ago, an alpha release was made. So this snippet you're seeing is going to be obsolete soon with the 5.3 release. Basically, you have to set up an effect handler, an exception handler, and a continuation as to what you have to do once an effect is being performed. All these slides are available online on our website, so you can take a look at these snippets closely once again. Question is, I think by now you get the idea that exceptions when exceptions can be resumed, what you have is you end up with effect handlers. So what approach can you take what approach can a compiler engineer take to implement such a language primitive? And two of the most popular approaches are continuation passing style, which is basically transforming your imperative code into continuations and making sure you can interrupt them in between. This can happen, and the popular implementations of CPS are actually in the user space itself. And I believe Haskell has a library called Polysemy, and I believe there are many libraries like that. But what they do is in the user space, they turn your computations into continuations and break down your control flows so that you can switch back and forth from one point to another. Continuations in programmer parlance is nothing but callbacks. They're just functions. So as you can see, the biggest problem with such an implementation is that you end up with a lot of free variables in your functions, creating a lot of closures. So you'll end up having a lot of heap allocations, which you might want to avoid if you're sensitive about your, especially when you do systems programming. So OCaml decided to go ahead with the other most popular approach to implementing effect handlers, which is delimited continuations. Delimited continuations are like continuations, except for the fact that you can pause or until a prompt you can suspend a certain continuation. If you're able to suspend a continuation, you can just say that you have taken the delimited continuations approach to it. There's a lot of theory behind this. We'll try to skip a lot of it, but the basic idea here is you can think of. I'm sure a lot of people here are familiar with assembly. You can think of if you consider CPS to be the go-to of the compiler world or the implementation of effect handlers. You can delimited continuations all return. You can jump to a place and then come back. unlike continuations, which just resume your computation. So that's just in short. Let's get the meat of this talk, which is the OCaml compiler internals, and let's try to understand what the problems are. And I have a small little animation here with some code to help you understand what the problem here is. So here, what you see here on the screen, and I guess I'm not sure if they're still visible. But the idea is that uh, when you when you have exceptions, you progressively build stack frames, and then at the point when you throw an exception, you just cut back the stack to a state where the exception handler was installed. So you see, you can discard the frames because you don't need them anymore. There's no question of the control flow being resumed from the point where exceptions were thrown. Whereas with effect handlers, that's not true anymore. You might build up stack frames like this, but once an effect is performed, you might have to go back. And when you go back, you have to make sure their stack frames are in that same state as they were. So yeah. So as you understand, simply put, it's a bookkeeping problem. How do you make sure you restore your stack back to that state? So OCaml came up with this layout of a new layout for the stack frames, and program stacks, by the which for OCaml frames are no longer on the OS handed program stack. It's now allocated on heap. So yes, you have heap allocated stacks for OCaml now. This is what the structure looks like. And as you see, this is going to be, it's far too technical to discuss each of those struct handlers right now. But the idea is that there are some headers in the stack that help you identify, describe your fiber, and which contain frames. The yellow blocks represent OCaml frames. And then you have this thing called a red zone. Very quickly explained, the red zone is a way for the OCaml stack to make sure you're not overflowing, because you don't have the guard pages anymore that were created by the OS for you, because these are now all allocated on the heap. So the red zone is a way. Red zone is a way to make sure you're not overflowing you're overflowing your allocated stack. B, it's also a small little optimization trick that OCaml uses for the leaf nodes in your call graph, so that where you can make sure that if something doesn't exceed the space needed on the stack, you need not worry about checking for its overflow later on. More on this maybe some other time. So let's quickly look at what a program now looks like. So like before, we have, as we enter deeper and deeper function calls, frames get allocated. But now once you enter an effect handler, you now allocate another program stack on the heap and start with the same metadata layout, and proceed with the rest of your program over there, and keep allocating frames on that stack now until you finish it. So this is probably a lot for a 20-minute talk, but if you'd like to learn more about it, I have compiled all my notes on this particular link. And where you can find the compiler overview, the passes involved, and the generated assembly. Most of the generated assembly is in ARM64 because I was using a Mac, but I'm sure you can always reach out if you have any difficulty. So yeah, thank you for listening. Here are my details if you'd like to reach out, and I'm happy to answer questions if you have any. I'll try my best, that is.
Uh, Thank you for the talk. I have very limited experience in OCaml, but thank you for also maintaining easy package manager. Dune and OPAM are very difficult to actually get started with. I have a few talks aside from the talk itself. What do you think about like ML based languages, and how they can become how they can be, what could be the argument to use it in the mainstream, because everyone here uses system level languages, right? For most of the part, hopefully. uh, So, what do you think? What are the good parts of ML-based languages, and what are your gripes? One of my few of my gripes is actually like exiting out of functions, what in a for loop, for those kind of things would be my small things that I like for OCaml or ML-based language to improve on. But yeah, that's obviously comes with functional style. So, what would be your place to be? What is the pros and cons of ML-based language for a system?
Yeah. So I think almost a lot of people these days are realizing the value of type systems, strong type systems. So if you understand that, then OCaml offers the same type safety that Rust does. I'd like to take Rust as a reference here because Rust is a lot of people know Rust. When you opt into a managed automatic memory management, what you have is you have this freedom to have much more expressive abstractions, and you can think you can afford since you can afford a GC, you can think at a higher level, a level which a lot of people are comfortable with, rather than having to worry about, oh, whether did I borrow this piece of slice of array or not, or you can rather go after certain abstractions that are much more readable, when functions as first class is not a big thing to worry about. So major applications are those major applications are in that domain, which don't worry too much about allocations. For this crowd, I'd say OCaml is a great language for writing compilers, because not only does it have a very nice parsers like Menhir, which provides you like a pure function interface, unlike Bison and other LR generators, which are like very imperative. You have a lot of stuff going around, difficult to compose. So that's one reason I would say you could opt into OCaml. Other reason would be simply any place you can afford a GC, you could opt into OCaml.
Thank you for the talk. Any quick example of when you would need the red zone? I mean, when would the compiler not be able to determine the right size of the stack frame and you would overflow regardless?
So I guess I spoke a bit in a hurry. It's the red zone is actually to make sure the red zone is like a safe buffer space for the leaf nodes in your call graph. So then that's when you can skip the memory checks. So as you know, now there used to be a guard page from the OS 100 stack, and you don't have that anymore. So what would happen is you'll have to have that overflow checks in the in the epilogue of the in the prologue of your yeah. Only for the leaves they take advantage of the red zone. So you can skip all your overflow checks for all those leaf nodes. And when they benchmark, they notice that this is good enough for you to this is good enough optimization trick. And a lot of function calls happens at the leaf node. I believe this is all. By the way, all this is work from a team at IIT Madras. So I mean, all the credit goes to them for doing all the benchmarking, all the runtime implementation, etc.
Yeah. So you said that continuations are like callbacks. I'm finding it hard to visualize that. Why did you say that? On what basis?
Perhaps you did not uh, like deep into it, because my idea was to bring an analog. So continuations are, as I understand, a very useful concept in design of programming languages.
That I agree with.
Right. But for us programmers, when we try to visualize, we don't have anything. We don't deal with continuations. But if you tell us that CPS is something that turns your programs into callbacks inside callbacks inside callbacks.
How is it callback? I mean, that's my question.
Okay.
Callback is your calling of.
Yeah.
function,
Sorry,
yeah.
I see why you're asking this.
Yeah.
When I say callback, I mean a first-class function that JavaScript programmers are used to passing. We call it callback-driven API, where you request a resource, and the requested resource is available at a later point in time, and you access it via a function. So if maybe the terminology is a bit quite overloaded and it can mean something else in some other community, but at least in the JavaScript community, a callback is just a function.
So I know callbacks are always functions. Are you saying that the caller passes a function which is called by the callee?
Yeah.
Is that the?
Yeah. Technically, they get scheduled later by the scheduler.
Yeah, that's fine. Okay, fine.
So please come back for the next session at 2 o'clock.
There are few announcements. So after lunch, there won't be the session by Das Darshana will not happen. So the last talk by Divyanjali Sharma will move to the third session, and we'll have a break after that. Yeah, that's the announcement. And lunch will be served in the floor below. Yeah, please come back after lunch. Thank you.